Okay, so now we have a couple of remarks here. So we have some, now I think this color must be changed to this color. We have a couple of remarks here, and the remarks are that we know from chapter 1 that if y is equal to f of x is an invertible function, then f inverse of x is equal to f inverse of y. Okay, so number 1, we know from chapter 1 that if f of x is equal to y is an invertible function, then so here we are saying that f of x is equal to y, then f inverse of y is equal to x, which is then f inverse of y is equal to x. That means that basically the inverse of f is the f inverse function, and you can see that basically the function f you supply it with x and it gives you y, and the f inverse function you supply it with the same y and it gives you back x, right? Now thus the graph of sine inverse function can be obtained from the graph of original function by interchanging x and y axis, meaning that, as you can see, basically what this function f of x does is that you give it x and it gives you y, right? Meaning that, for example, let's say that you have some function over here, and the function is for example, let's say f of x is equal to x cubed. Now f of x is equal to x cubed is some function like this. You have basically some function like this, right? So that is your y-axis, that is your x-axis, and this function that you get here is, well, more or less f of x is equal to x cubed. Now if f of x is equal to x cubed, then suppose that now what this function does is that whatever x you give it, it basically raises that x to the third power, and that becomes the output of the function. For example, if you give it 1, it raises 1 to the third power, you will get a 1 here. If you give it, for example, 2 raised to the third power is going to be 8 here. If you give it 3 raised to the third power is going to be 9 here, and so on and so forth. On the other hand, if you give it -1, it will give you -1. If you give it -2, it will give you -8, and so on and so forth, right? That means that the inverse of this function is going to be some function that if you give it basically the cube root of that if you give it x cubed, it's going to give you x, meaning that it has to take the cube root of your input, so that, and then it gives you some output, which means that in this case f inverse of x is going to be equal to the cube root of x, right? Which means that, for example, if you give this function some input like 1, so for example in the case of f of x, which is equal to x cubed, if you give it 1, if x is equal to 1, then x cubed is going to be equal to 1 cubed, which is equal to 1. If your x is equal to 2, then 2 cubed is equal to 8. If x is equal to 3, then then 3 cubed is equal to 27. I made a mistake here. 3 cubed is not equal to 9 but 27. And so on and so forth. Which means that if I take this output of this function and give it to this function, meaning that if I have the f inverse of x is equal to the cube root of x, and here if my x is equal to if my x is equal to 1, then the cube root of 1 is equal to 1. Then if x is equal to, for example, 8, then the cube root of 8 is equal to 2. The same input here. If x is equal to 27, then the cube root of 27 is equal to 3. Same input, and so on and so forth, right? Now, it so happens that if you actually do the graph, if you basically draw the line f of x is equal to x, which is a line which is at an angle of 45 degrees with the positive direction of the x-axis, the inverse of this function happens to be symmetric about this line, right? Meaning that if I just simply draw the graph of the function f of x is equal to x cubed, if I simply draw the graph of the function f of x is equal to, the cube root of x, which I don't know how to write, but we could hopefully find it over here. That's histogram, dot plot, box plot, normal distribution, t-distribution, Poisson distribution, binomial distribution, PDF, CDF, inverted. These are related to, I think, I don't know what they are. But if I do the cube root of x, you can see that you will get a function like this. And it is actually a function, meaning that it's a 1-1, and also depending on how you define it, it could be onto as well. Although I think the output goes all the way up to positive and negative infinity, right? Meaning that you can take the input, the domain as R, and you can take the range as R, so that the function is defined there. Now, if I do the graph of the function f of x is equal to x cubed, you will get some function like this, as you can see, right? And then if I do the graph of the function f of x is equal to x, you can see that the two functions are symmetric about this line. You see that, for example, if I draw a 90-degree line, if I draw a line perpendicular to the line f of x is equal to x at any point, the line is going to intersect the graphs of the two functions at the exact same distances from the line f of x is equal to x, which means that the two functions are actually symmetric about this line. And this function is when two functions are symmetric about the line f of x is equal to x, that means that basically so f of x is equal to f of x is equal to x, or y is equal to x, is basically a function that when you give it x, it will give you the same value for the output, or y. Meaning that you can see that, for example, 4, 4 is a point on the graph of the function. or for example 6 comma 6 is a point on the graph of the function. And what that means is that when the graph of a function is symmetric about this line, then you can actually get the equation of the other function by taking the x and y coordinates of all the points on the graph of the first function, interchanging them, and then taking x as y and y as x, and then that way you will be able to get the equation of the second function, right? And that's exactly what we are discussing here. We are saying that basically what we are saying is that so we said that basically y is equal to f of x. We said that y is equal to f of x is an invertible function if basically this function is an invertible function, right? Then x is equal to f inverse of y, and basically this is going to be basically the inverse of this function, right? Meaning that the input of this function is the output of this function, and the input of this function is the output of this function, right? Meaning that f inverse is the inverse of f. Okay, so what this means is that basically you can say that if a comma b is a point on the graph of the sine function, is a point on the graph of the sine function, then b comma a becomes the corresponding point, becomes the corresponding point on the graph of the inverse of the sine function. And the graph of the inverse of the sine function, of the sine function. Thus the graph of the function y is equal to sine inverse x. Thus the graph of the function y is equal to sine inverse x can be obtained from the graph of y is equal to sine x, from the graph of y is equal to sine x by interchanging x and y axes. The x and y axis, right? So the graph of y is equal to sine x and y is equal to sine inverse x are given in these two figures. The dark portion of the graph y is equal to sine inverse x represents the principal value branch. Now basically create the graph of the function y is equal to sine x, what I will get is basically f of x is equal to sine x, right? So that is this graph, this purple graph is not purple, but whatever the color that is, I don't really, that's something like blue and purplish blue or something like that. The sine function is basically this function here. Now if I draw the graph of the function y is equal to sine inverse, I don't know what to do with sine inverse here. The function sine inverse trigonometric sine inverse of x, and as you can see, the graph of this function is basically only a branch of the graph of the function y is equal to sine inverse x, and this calculator basically is working based on our conventions in mathematics, that we said that basically in that we were going to actually take the we said that we were going to since basically the sine function is a function that is defined from r to the closing interval -1, 1, right? So the function is going to be something like this. The function is going to be something like this, and you can see that the function is not 1, 1. For example, at this point the output of the function is 1, at this point the output of the function is 1, at this point the output is something like, I don't know, 1.8, 1 point something. This point over here, this is pi by 2, 1. At this point you have 5 pi by 2, 1. You can see that the inputs are different, the outputs are the same, meaning that the function is not 1, 1. So we said that what we would do is that we would take the function from negative pi by 2 to pi by 2, right? And if I take the function from this, basically from this point all the way up to this point, then what happens is that then you can see that the output of the function becomes -1. Over here the output of the function becomes 1. Now this output has become input for this function, for this red function, which is essentially the inverse of the purple function, and this function basically for -1. So over here you can see that the input has become -1, the output has become +1. And for -1 you have the output negative pi by 2, which is something about 1.5, 1.6, 1.7 or something like that. For this output you have basically 1 comma pi by 2. You can see that over here this is 1 comma pi by 2, this is -1 comma negative pi by 2, exactly meaning that exactly if you take this point and swap the x and y coordinates of the point, you will get exactly this point in the coordinate system. Moreover, if you take this point pi by 2, 1 and swap the x and y coordinates, you will get 1 comma pi by 2, which would be 1 comma pi by 2, as you can see over here, which is pretty amazing, as you can see. Now, so what we said was that basically we said that we would take the sine function as since from r to this set the function would not be 1, 1. We would basically define the function as negative pi by 2 to pi by 2, right? And then the function, the range of the function becomes -1, 1. Now, since this is the case, then the sine inverse function is a function that becomes a function that goes from negative 1 comma 1 to negative pi by 2 comma pi by 2, right? Negative pi by 2 comma pi by 2. And then this branch of the sine inverse function, we call it the principal, I don't exactly remember the term, but it was called the principal value branch. It's called the principal value branch of the sine inverse function, right? So that is that. And so the graph of, so we said that the graphs of y is equal to, so we said that the graphs and everything, and the dark portion is basically, what they mean by the dark portion is essentially this point over here, which I showed you on here, which is basically goes from 1 comma pi by 2, 1 comma pi by 2, and over here you have negative 1 comma negative pi by 2, which is basically, this is what they mean by the dark portion, right? And that is what they're saying is that the dark portion of the graph of y is equal to sine inverse x represents the principal value branch. The principal value branch is basically this part over here. Again, I repeat that the principal value branch of the sine inverse function is exactly this red part over here of the sine inverse function. Otherwise you would get the whole sine inverse function. Let me see if we can actually do that. Maybe this calculator will give us something. Sine inverse. Let's see if that gives us. Arc sine inside arc sine of x. It doesn't work that way. I reload it. Distance, midpoint, parallel, perpendicular, tangent. Oh, how do you get more? How do you get more here? I don't know how this calculator works, but normally what you would get is that you can imagine that this whole function is basically moved in a counterclockwise direction. In a counterclockwise direction by 90 degrees, and then you would get the whole function something like this, meaning that you would get the whole function as a function something like this, something like this, instead of, rather than getting the function basically the sinusoidal function this way, you would get it this way. And of course, the principal value branch would of course be this part of the function that we saw basically right here, right? This is the principal value branch of the sine inverse function. Okay, so that is basically, that is that. Now let's now talk about the second remark here. Okay, so remark number two Remark number 2 is that it can be shown that the graph of an inverse function can be shown that the graph of an inverse function can be obtained from the corresponding graph of the original function as a mirror image, which is basically a reflection along the y is equal to x. This can be visualized by looking at the graphs of so let me write this down. It can be shown that the graph of an inverse function can be obtained from the corresponding graph of the original function, as a mirror image, or reflection, that is reflection along the line y is equal to x, along the line y is equal to x. Make sure there is no parentheses here. Line y is equal to x. This can be visualized by looking at the graphs of y is equal to sine x and y is equal to sine inverse x, and we already talked about that and so like the sine function, the cosine function is a function whose domain is the set of all real numbers and the range is the set. So when we were talking about the cosine function, so we said that basically the cosine function is a function whose domain is R and the range is -1 to 1, right? Which means that again you will get into the problem of the function not being 1, 1 and so on and so forth that we talked about in the case of the sine function. And what that means is that basically if you want the cosine function to be an invertible function, we have to restrict the domain to some values. So let's see how we can restrict it. So now if I draw the graph of the cos function, actually it's supposed to be cos x. So you can see that the function is, you can basically restrict the function from 0 to, for example, pi. You can restrict to 0 to pi, or you can go, for example, 0 to pi by 2. You can go from pi by 2 to pi. In all of these intervals, the function is 1, 1. You can go from pi to 2 pi, meaning that you can go from pi to, or pi from pi to 3 pi by 2. You can go from 3 pi by 2 to 2 pi. It doesn't matter what you do, but you cannot, for example, choose -pi by 2 to pi by 2, because in this interval, as you can see, the function is not 1, 1, meaning that, for example, over here, the function, the output is somewhere over about 0.56, and the input is somewhere about 1.04, and this is about the same output, but the input is the negative of the exact same input, which means that the function is not 1, 1. So we have to restrict the domain of the function so that the function is 1, 1, and the function is already onto if we talk about the range of the function from -1 all the way up to +1, and then that way the function is going to be invertible. Now, if we restrict the domain of the cosine function to, for example, 0 to pi, as you can see in this interval, the function is 1, 1. Then it becomes 1, 1 and onto with range -1, 1. Actually, the cosine function restricted to any of the intervals. For example, you can go from -pi to 0. You can go from 0 to pi. You can go from pi to, for example, 2 pi over here to here, etc. You can just keep going. The function is taking any of these intervals and taking the range as -1 to 1, the function is going to be both 1, 1 and onto, which means that the function is bijective. The function is injective and surjective, meaning that the function is bijective. And so we can therefore define the inverse of the cosine function in each of these intervals, right? So we denote the inverse of the cosine function by cos inverse, or the arc cosine function. So the inverse of the cosine function we denoted by arc cos or arc cosine function. Arc cosine function and arc cosine function. That's cos inverse, or you can just simply call it cos inverse. Thus, the cos inverse is a function whose domain is -1 to 1. So since we argued that basically we have to restrict the domain of the function, I can say that the cos function, for example, I don't know, you can take any interval over here as long as the function in that interval is basically 1, 1. And once you take that interval, then that interval has to be mapped to some other interval, for example, -1, 1, which is the range of the function. And so you can say that the cos inverse function, this is supposed to be the cos inverse, of course. So you can say that the cos inverse function is a function whose domain actually has to be this one if it's supposed to be the cos inverse function. So I have to use this as the domain of the function -1, 1, and then I have to map this to some interval here. For example, the interval 0 to pi, for example, right? 0 to pi. And in this interval, the function is 1, 1, right? And so we can say that basically the cos inverse function is a function whose domain is -1 to 1, the closed interval -1 to 1, and the range could be any of the intervals. For example, you could pick -pi to 0. You could, actually these are closed intervals. We could pick, for example, 0 to pi. You could pick, for example, pi to 2 pi, and so on and so forth, right? And of course, corresponding to each of these intervals, we get a branch of the function, cos inverse. We can argue that corresponding to each interval, we will get a branch of the cos inverse function, right? the branch with range 0 to pi. So now if I take one of these branches, so if I say that the cos inverse function is a function from -1, 1, and that to the range 0 to pi, so this branch, so the branch with the range 0 to pi is called the principal value branch. It's called the principal value branch of the cos inverse function. And we write basically the cos inverse is a function from -1 to 1 to 0, pi basically. And the graph of the function given by y is equal to cos inverse of x can be drawn in the same way as discussed about the graph of the basically the sine inverse function. The graphs of the y is equal to cos x and y is equal to cos inverse x are, we will actually do them. So, and one thing that you need to pay attention to here is that here you can see that the f of x is equal to cos x is basically this function here. Now, if I draw the graph of the function f of x is equal to cos inverse function, and that is equal to f of x is equal to cos inverse of x. As you can see, so over here the function goes from -1 and -1, pi, and the function over here you have it at 1, 0. So that means that this is basically over here we said that the function, the domain of the function goes from -1 to 1. That means that the domain of the function goes from -1 to 1, which is basically -1 over here and 1 over here, and the range of the function goes from 0 to pi, which means that 0 and somewhere pi is 3 point something, which is this value over here. And if I draw this line over here, you can see that I think if you think about basically this part of the function, it's symmetric about this line. If you think about this line, for example, from somewhere over here all the way up to somewhere over here, so then they would be symmetric, and that's basically the graph of the function f of x is equal to cos inverse of x. So one important or one interesting thing that you can see here is that the function basically the original function is cos, which goes from 0 to pi, to -1, 1, and you can see that basically if I 0 to pi basically is you can see that basically this is the part of the function that we are talking about from here all the way up to here, and then this point, if I take this point symmetric, is if I find the image of this point 0, pi, -1, if I find the image of this point through this line, I will get -1, pi, which is basically this point over here. And the other part basically, which is 0, 1, if I find the image of this point through this line y is equal to x, I will get 1, 0, which is this point over here. So you can see how the two functions are symmetric about the line y is equal to x. Now, so basically the graph of the functions, we already did the graphs of the functions, and the graphs of y is equal to cos x as y is equal to cos inverse x are drawn here as well. Now let us discuss the cosecant inverse and secant inverse as follows. Okay. So now we want to talk about the cosecant inverse function and the secant inverse function. The cosecant inverse function and the secant inverse function. These two. So basically you know that the cosecant of x is equal to 1 over sine x, and the domain of the cosecant function is the set. So the domain of, or you can basically say that the cosecant function, the cosecant is a function that goes from basically wherever sine is 0, you have to exclude those points from the domain of the cosecant function. Now sine is 0 at 0 and pi, meaning that at pi, 2 pi, 3 pi, and so on and so forth. So that means that I have to write here basically the set of real numbers minus the set x such that x is equal to n times pi, where n belongs to the set of integers, right? Meaning that every multiple of n has to be excluded from the set of real numbers, and then that becomes the domain of the cosecant function. And the reason for that is that basically at these points, for example, let's say at n is equal to 0, then x is equal to 0, at which point sine is equal to 0, cosecant is undefined. At n is equal to 1, then x is equal to basically pi, at which point basically sine is equal to 0, and then cosecant is undefined, and so on and so forth. If you take n as equal to -1, then you will end up with, for example, x is equal to negative pi, and at negative pi again sine is equal to 0, cosecant is undefined. So I have basically simply taken out all of those points out of the set of real numbers so that we can use that set as the domain of the function. Okay, so basically we said that the domain is basically this function, this set. So I can write the same set as this is the domain of the cosecant function, right? So so basically you have r minus all x such that x is equal to n pi, and n belongs to z. So what that means is that you can rewrite the same set as basically the set of all x, such that, for example, x belongs to r, and x is not equal to n times pi for all n belonging to z. Right? I can write the same thing in the same way, meaning that x belongs to the domain of the function is the set of all x, such that x belongs to the set of real numbers, except that x is not equal to n pi, where n belongs to the set of integers. So that is basically the domain of the function. The range of the function, the range of the cosecant function, we said that basically it is basically let me take a look at the function here. The cosecant function is basically r minus, you can say r minus the opening one, -1, comma 1. Meaning that we saw that basically the function was basically, now I don't remember where the asymptotes are, basically do occur at n times so pi, meaning that, for example, the function would be, this is pi by 2, this is pi, so that would be one of your asymptotes, and this would be again another asymptote here. So again, at 0 you have another asymptote. Over here you would have another asymptote. That's all the multiples of pi. You will have asymptotes all across the domain of the function. And this is your y-axis, this is your x-axis. And we saw that basically for x is greater than 0, for x is greater than 0, you're actually calculating the 1 divided by the sine of a positive angle, which is positive. So then that means that basically you would get some function like this. You would get some function like this, and then for x's, when x is above 180 degrees, basically the sine becomes a negative value. So you would get a function like this. When x is basically negative pi by 2, you will get again a function like this, a positive value over here, and so on and so forth, right? So that would be the cosecant function. And as you can see, between -1 and 1, so of course the function has some values here and some values here, but between -1 and this is negative y is equal to -1, this is y is equal to 1. Between these two lines, the function generates no output, which means that the range of the function can be written as r minus -1, comma, -1, comma 1. Now, if we come back to the function here, I can write the range of the function as basically the range can be written as the set of all y, such that y belongs to the set of real numbers and y is greater than or equal to 1, or y is less than or equal to -1, right? Y is greater than or equal to 1, or y is less than or equal to -1. That is basically the same set that we talked about here. So that means that basically y is equal to cosecant x assumes all real values except for, basically meaning that y is equal to cosecant x assumes all real values except for -1 less than y less than +1, and is not defined for integral multiples of pi. Moreover, y is equal to cosecant of x is not defined for integral values of pi. And integral values of pi means that basically x is we said that x, the domain is basically all x such that x belongs to R, but x is not equal to n times pi, meaning that n is an integer, so these are all the integral multiples of pi basically, right? So what that means is that so now we saw that basically the cosecant function basically looks something like this. If I use this graph over here, and graph y or f of x is equal to cosecant x, you can cosecant CSC of x. If that is the case, so you can see that basically the function of course has to be 1, 1, otherwise the function is not invertible. So you can see that, for example, in this interval 0 to pi, so for example 0 to pi, the function is not 1, 1, because you can see that, for example, you have the same outputs here for different inputs. You can, however, for example, go for negative pi by 2 to pi by 2 between these two values for the domain of the function. The function is 1, 1. Over here the function is basically, as you go towards the positive axis, the function is decreasing, and starting from 0 the function is again, it jumps to positive infinity, again decreasing to y is equal to 1, right? Which means that you can go for example, some value like negative pi by 2 to pi by 2. You can go for example, you can restrict the domain to 0 to pi by 2. You can restrict the domain to pi by 2 to 0, and so on and so on. You can basically restrict the domain to negative 5 pi by 2 to negative 3 pi by 2, and so on. You can do whatever you want to do. But basically, now what we have ended up doing in mathematics is that we have restricted the domain of the function. We have restricted the domain of the function to negative pi by 2 to pi by 2. And as you saw over here, basically between negative pi by 2 and pi by 2, the function is 1, 1. And it is also unto considering the fact that we have to somehow take out all of these values between negative 1 and 1, right? So and of course we have to take out 0 as well, meaning that at 0 your function has no output, right? So we have to take that out as well, and because otherwise it would be no function really. It would really be no function if 0 is not mapped to anything. It would be no function. So now if we restrict the domain of the cosecant function to negative pi by 2 to pi by 2 minus the set containing 0, then it is 1, 1 and unto with its range as, then it's going to be 1, 1 and unto, 1, 1 and unto with range as basically the set R minus negative 1 to 1. So we have to take out those values as well. And so then basically you can find the inverse of the function. Now, of course, we argued that you can of course restrict the domain of the function to anything. So for example, you could do the same thing with, for example, negative pi by 2, which is somewhere over here, to, for example, negative pi by 2. You can restrict it to this domain as well, and then of course you have to take so this is pi by 2, this is pi, so this is negative pi, so you have to restrict it to negative 3 pi by 2 to pi by 2, but then you have to get rid of this pi over here and take it out from the domain of the function. Or you can go from negative pi by 2 to pi by 2, and then you have to take 0 out, right? Or you can go for pi by 2 to 3 pi by 2, but then you have to take the pi out, right? And well, depending on your needs, of course, you can do so. There is no problem with that. But standard way of doing it, meaning that when we talk about in a standard way, when we talked about the cosecant function, we say that the cosecant is a function from the set of real numbers. From the set of real numbers, and we take out all the integral multiples of pi x, such that x is not equal to x, or x is equal to basically n times pi, such that n is equal to n belongs to the set of integers, right? So that is the domain of the function, and the range of the function becomes basically the set, all the real numbers minus that interval that contains all the numbers between -1 and 1, which is basically r minus -1, 1. So that is the standard way of, that is what we mean when we normally say the cosecant function. Now when we say the cosecant inverse function, we have to move this around, meaning that I have to say that the domain of the function is basically r minus basically this set over here. Actually, I think I've made a mistake here. This is not supposed to be a set. This is supposed to be an interval, right? So then I have to write it as -1, 1 to the set that contains negative pi by 2 to pi by 2, meaning that we restricted the domain of the function to this interval, right? So we say that basically the range of the function is the same thing, which is r minus the open interval of -1, 1, and then the domain of the function, since we restricted that to these numbers, we have to go from negative pi by 2 to pi by 2, and this is a closed interval, and I have to subtract from that basically 0, or the set containing 0. That is what we mean when we say the cosecant inverse function, right? So now if we draw the graph of the cosecant function, let's draw the graph of the cosecant function. Let's see what we get. So when you draw the graph of the cosecant function, of course you will get this graph, and we said that we would restrict the domain of the function to negative pi by 2 to pi by 2 except for 0. So that is the domain of the function, and the range of the function goes from negative infinity all the way up to positive infinity, except for these numbers from negative 1 to 1, excluding negative 1 and 1, of course. Now if I draw the graph of the cosecant inverse function, which is actually not here, I have to do it on this graph. So if I do the graph of the cosecant CSC of x, CSC of x is going to be this graph over here, and CSC inverse, let me see if I can find that here. Cosecant inverse of x, you can see that you will get only these two parts, and you can see that this graph actually goes from 1 comma pi by 2 and goes all the way up to infinity comma, and it basically the line gets closer and closer to the x-axis, and over here you have negative 1 comma negative pi by 2, and then the line keeps getting closer and closer to the x-axis, and of course on the negative side, which means that basically remember that basically the cosecant function, which is basically this blue purplish function that we have here, we took basically negative pi by 2 to negative 1, and we went all the way up to pi by 2 to pi by 2 comma 1. That means that if I change the x and y coordinates of this point, I will get negative 1 comma negative pi by 2, which is basically this point over here, negative 1 comma negative pi by 2, and then it keeps going in this direction, right? And this point over here I have pi by 2 comma 1. If I change the x and y coordinates of this point, I will get 1 comma pi by 2, which is this point over here, and then it goes all the way up to basically on the x-axis. You can just keep going towards the positive infinity across the x-axis, and what that means is that basically the function. What that means is that the function is actually. What that means is that the function is actually symmetric about this line, right? Because you get this part over here, okay, so we said that the function is symmetric about this line, meaning that this part that is basically pi by 2 comma 1, this line going up here, if you take the image of this line, this curve through this line y is equal to x, this slanted line, you will get this part over here. And if you think about this curved path over here, this curved line over here, and if you take the image of this line through the image of the curve through the line y is equal to x, you will get basically this curve over here. And so again, the function is symmetric about the line y is equal to x, right? Now, and so basically the principle, there was something that we talked about, which was basically the principal value, I keep forgetting the name. the principal value branch of the cosecant function is actually all the parts that you see over here, because well, because the function is I mean the reason why that is that basically the calculator is giving us only the part which is actually defined in mathematics, and in mathematics only this part is defined. So this is the principal value branch of the cos inverse function, right? Now otherwise you would see a whole bunch of lines over here going up and down, I mean in a horizontal direction, all the way from negative infinity to the positive infinity. For each of these you would have the same line basically shifted or rotated 90 degrees, for example, counterclockwise or something like that. But the calculator is not doing that, because it's giving you only the part which is actually defined in mathematics. The rest of the function it's actually ignoring it. Okay, so that was basically the cosecant function. That was the cosecant function. Meaning that, what I mean by that is that what you would get would actually be something like this, meaning that this is the graph of the cosecant function, and this would be the graph of the cosecant inverse function. And as you can see, these dark parts over here are only this part, and this part is only the parts that have been given us by the calculator. The calculator has ignored all of these parts that, for example, this part here, or this part over here, or this part over here, they all have been ignored by the calculator. So that was all about the cosecant function. Now in the next video we will talk a little bit about the secant function, and so I will see you in the next video, and thank you.